and 3. The idea of magnetic force, listen gentlemen, the idea of magnetic force is similar to that of electric force. So if you think back to electric force was exerted or was felt when there were two charged particles. Okay, either the force was attraction or the force was repulsion. Okay, that's when we had two charged particles. Now we're going to take a look at a magnetic force that occurs as a result of not two charged particles, but a charged particle and a magnetic field. Again, think back when we had electrical stuff, we had two charged particles. One could be, let's say, positive, one could be negative, so the force between them was attractive. The electric force was Q1, Q2 over R squared. Now, we're looking at magnetic force. We don't have two charged particles of magnetic force. Here's what we have. We have a magnet that exhibits some field lines. The actual charged particle interacts with that magnet, but not both of them, simply one of them. They both can, but they're not needed. Okay? So again, for there to be a force on a particle from a magnet, that particle needs to be charged, but only one particle here. This is similar to electrical stuff because with electrical, we needed two particles. One was like the source, the other felt a push or a pull. Here, the magnet is now like the source. And this single particle now is feeling a push or a pull or some sort of a movement. And we'll talk about specifically how that movement works. Okay, so let's take a look. Kean, why don't you read for us, nice and loud.
I'm still going at
Just off here, it's fine.
From experimentation, it is seen that the stationary charged particle does not interact with a constant magnetic field. Yet a moving charged particle does.
Alright, pause there for 1 second. So the first thing we want to recognize is this. A charged particle is, or interacts, or is feels a magnetic field if it's moving. Okay? Make sure we underline that. It's got to be moving. It's got to be moving. Keep going.
Okay, the force experienced has a maximum value in which charging moves perpendicular to the field, decreases at other angles at zero. The particles move parallel to the field.
So let's say we have a magnetic field, okay, and we'll say that the magnetic field is to the right in this case. Our field lines look like this. Put it away. Put it away. Johnny.
What?
Put it away. Put it away. So if you have a particle here, I mean, that's stupid.
No, I was trying to pour it myself.
So we have a particle here. Now, if this particle is stationary, it's not going to feel any sort of a magnetic pull because it's stationary. Now, if I start, and I put a positive, it's a positive particle for this case. If this particle started moving, it feels a magnetic force the most if it is moving perpendicular to the field. So, for example here, if the velocity is either up or down, this particle will feel the magnetic field's pull. But if this particle is moving left or right, it will not feel it. Because if it's parallel to a field, it does not feel any sort of a pull on it whatsoever. I scarfed that lunch, it's killing me. You ready to eat lunch real fast? That was a wrap. And you got something to do? So, if this particle were moving left to right, it would not be affected by the magnetic field at all. It would just move on its own, left to right, the way it was moving. If the particle was moving up or down, it would be affected the most it can. If the particle is moving at some arbitrary angle, it's somewhere in between. We're specifically going to look at when a particle is moving either perpendicular or parallel to a field. Okay, the in between has to do with trig. So you just use your sine and cosines again. That's all you would do. Okay, we're not going to do that, it just said. So listen, please. Okay, again, we're doing only with perpendicular and parallel motion. So let's take a look first for a magnetic field. B, capital B, is the variable for a magnetic field or magnetic field strength. Again, B is magnetic field strength. F mag stands for the force of magnetism, clearly. Q stands for charge, clearly. We've done these. We haven't done F mag, we call it magnetism now. And then V stands for the velocity of the object. Okay, the denominator should not be anything new at all. Q and V are things we've seen. So this is our relationship. Now, the variable that represents a Newton per coulometer per second is called Tesla. Tesla. Why does that ring a bell?
Car. The electric.
Everybody thinks about the car, but who's it named after? Nikola Tesla. Okay? One of probably the smartest, seriously, probably one of the smartest scientists, engineers, physicists that ever lived. A lot of people consider him to be smarter than Newton, smarter than Einstein.
No way.
Yeah.
What did he do?
Tesla is, here's the thing about Tesla. He's not known for a lot of things, yet he contributed to so many things. It's unbelievable. But he never took credit for stuff. He would do things, he would not publish them, he would keep the knowledge to himself, and then somebody would discover it 10 years later. So there's a ton of things that are existing today that are not named after him that he discovered before the first person that ever else discovered it.
So why didn't he help?
He was just a very quiet guy. I think he died early. I think he died when he was like in his late 20s or 30s or something.
So how is it?
He died very young. He was a genius. At like 18, he was doing things that most physicists had no idea what he was doing. He was like a pure genius, this guy. So he had a lot of theoretical projects that he studied on like energy specifically. He was all about E&M. Electricity and magnetism was one of his big things. And a lot of the projects that he worked on were about things like harnessing energy and using energy, using energy that could be reusable. Things like solar cells, those concepts of renewable energy, of concepts of never running out of energy, of using things to its maximum capacity. Tesla was there for a lot of that.
But if he never published that as anything, then didn't he not help like the rest?
Well, that was the thing. Like now, a lot of his papers have been actually made published. So a lot of them are public domain now. So now they're known, but then no, they weren't.
So then why didn't he do that?
I don't know the history too much about him besides that. That's what I've read about him. And I've read most of what I've read is like out of your textbook and like random searches online. But seriously, if there's a scientist that you've ever do like a project on, most people do like Einstein or Newton or any other scientist that you think about, Rutherford, because you know these names. Tesla is a huge one. So if there's a person you ever need to do a project for, I'd recommend Tesla. Okay, not here. But if you have like in college, if you take like a physics course or an astronomy course. Okay, right-hand rule. Let's take a look. This is the second right-hand rule. The first right-hand rule we learned yesterday. Yesterday or 2 days ago? 2 days ago. So the thumb points in the direction. This is the old rule. Thumb points in the direction of the current in a wire, and your fingers wrapped around the wire, showing the direction of the magnetic field around the wire. That was the right-hand rule for a current carrying wire. This is also called the right-hand rule, but it's for magnetic force. Clearly different things. So, your thumb in this case is similar to last time. Remember thumb pointing in the direction of the motion of the current? Well, now is the motion of the particle. So thumb points in the direction of the velocity or the motion of the particle. Your fingertips point in the direction of the magnetic field. That's B at the top. And F magnetic is the force that this particle would feel on itself. Okay, so in this case, we're looking, well, this is a positive charge. For a negative charge, it would go in the opposite direction. So if there's a particle, okay, take a look at your hand. Particle's moving this way, and the field we're acting up. What will happen is this: the particle will start to curl toward you, because the field is pushing it. Look at the magnetic force. Field is acting up, velocity is out, magnetic force is this way. So a positive particle that's moving this way would eventually start to come towards you, like out of the page. You're going to hear me say out of the page and into the page a lot in this section. So into the page literally means this direction, out of the page means this direction, then there's up, down, left, and right. There are 6 directionals. Into the page and out of the page is your z-axis. Okay, x is left to right, y is up and down, z, we say into the page or out of the page. Sure, you could say, but which is forward and which is back for to you? That's forward, I'm guessing, and that's back, right? Yeah, depends on your orientation there. So into the page, out of the page, same idea. Okay, so again, for a negative charge, it would not follow the right-hand rule. It would be the opposite. So, the magnetic force, instead of coming out of the page or out of your palm, would go this way. Into your palm or into the page. Alright, to do this, let's take a look at an example. Mullen, read it, since you're talking so much as it is. Let's go.
When a proton moves straight upward away from the ground through a uniform magnetic field that points east for the magnitude of 3t. If the proton moves at the speed of 2 times 10 to the 8 ms through this field, what force, magnitude, direction will act on it?
So think about this for a second. Draw yourself a diagram first. Draw what you think is happening, please. Draw your field lines as parallel lines with the label B. And it says here clearly that the field points east. We're told that the particle, a proton, moves vertically or straight upward. So we can draw the particle moving upward. So we should have velocity of the particle going up, the field going east. So already you should see this. This is what should be in your mind. Field is east, that's my fingers. My thumb is the particle's motion, that's upward. So the magnetic force is going to be, again, out of my palm. Out of my palm this time means what? What do we call this? Forward or into the page. Okay? So we know already which way the force is going to be felt. To draw that, here's your proton. It's moving up. Here's the magnetic field. East. The proton's velocity is very large, 2 times 10 to the 8 meters per second. The field strength is simply 3 Tesla. What is the force that we're going to feel, and what is its direction? Magnitude and direction. So start with your formula. Okay, M for magnetic. The magnetic field equals the magnetic force divided by the product of charge and velocity. What is the charge in this case? It's the only thing we don't really know. We're going to look for F. We know B. We know V. What is Q? What is Q?
1.6 times 10 to the negative 19.
Yes, the constant, aka 1.6 times 10 to the negative 19, the elementary charge. Okay, it's the charge. Why is that? Because it's a proton. It says it right here. A proton is 1.6 times 10 to the negative 19 coulombs. Solve this formula for the force. Okay, BQV. Solve for force is BQV. At this point, simply plug in to get the magnitude. This will not give us the direction. The direction comes from our right-hand rule. Even if I didn't remember, I should know that my units are, or if I didn't know, I should remember that my units are newtons because I'm looking for a force. If I didn't know that a Tesla times a coulomb times a meter per second turns into newtons, it's not a big deal because you're looking for force, so it's got to be in newtons if you're given your standard SI units in the problem. Multiplying these three things together, it's got to be something with a negative exponent because I see that I have negative 19 and only positive 8, so those aren't going to cancel. So it's going to be something with a negative exponent. It's what times what? Go ahead.
9.6 times 10 to the negative 11.
Okay? 9.6 times 10 to the negative 11 newtons. So, think about how small of a value that is. Such a small value. Consider, though, that in this case, what is moving? A proton. The mass of a proton is so small that if you know this is the force, and you use the mass of a proton, you can find the acceleration felt by that proton. Let's go ahead and do that. Take this force. Think about this is the overall force felt by the proton. The following is true. Force equals ma. I'm writing Fm for magnetic force here, even though it's F net, but it's the only force acting on it. Gravity is also acting on it, actually, I should say. So let's do this. Fm minus, well, actually, which way is Fm acting? It's acting to the right, so we'll leave it by itself. Let's find the acceleration felt. Anyone have either their textbook or anyone have their textbook with them? Does anyone carry them with them? No. Can somebody Google the mass of a proton, please? It's in your text. That's what I was asking. Google the mass of a proton. Thanks, sir.
1.67262.
Can you read the number or no?
1.78 times 10 to the negative 27.
1.7 times 10 to the negative 27. And the numerator is 9.6 times 10 to the negative 11. We have newtons over kilograms, thus giving us acceleration. We're going to get a very large acceleration here. Okay, we're taking a number like negative 11, dividing it by negative 27. So you technically have to do, when you think about your laws of exponents, negative 11 minus negative 27. So you're going to get something to the positive 16 or something like that.
5.6 times 10 to the positive 16.
16?
Yeah.
Look at the value of that acceleration. It's a very, 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 very large acceleration. Although the force felt by the proton is so small compared to what we're considering, like on a macro scale, on a micro scale, on a nano scale, I'm thinking about the fact that the mass of a proton is so small that this tiny force actually does a lot to it. Okay, and which way does it cause it to accelerate? Again, take your hand. Thumb is up because it was moving up originally. The field was to the right. So it's into the page. This, ready? Follow my hand. The proton is doing this. It's going to turn literally into the page. It was moving up initially, but the acceleration is this way. So it's going to start to curl into the page.
That would be ms squared.
Say it one more time. Would it be m?
Never mind.
Yes, it would. Meters per second squared. Thank you. Good point. Yeah, acceleration, meters per second squared. Make that correction. Thanks, Marco. Let's take a look at this now. This is pretty interesting. Look at the diagram on your own. Spend like 30 seconds. Look at the diagram and try and analyze the diagram. Put your thumb in the direction of the velocity. Put your fingers in the direction of the magnetic field.
I don't understand.
What do those X's mean? I'm going to
It's
explain.
like fingers. Man.
What do those X's mean?
The proton?
Have you ever seen this before? Either you see X's or dots.
Positive or negative?
I see X's.
No. Everybody sees X's. Some diagrams see dots. It's not like the colorblind test. It's like, do you see the letters in the test? It's like the kids who can't see are colorblind. No. Either in scenarios you see X's like here, or you're going to see dots. It's one or the other. So, think about this for a second. My gosh. Take a bow and arrow. Okay? Put an arrow on a bow and arrow. If I were to use a bow and arrow, right? And I were to fire the bow and arrow this way and let go, you would see the X from the tails of the arrow, wouldn't you? Stay with me, seriously. It's the easy way to know how to do this. You shoot a bow and arrow, you let go, it's going this way. You would see the tails on the feather, and you would see like an X. Assuming there's two feathers and they make an X, whatever. 4 feathers, right? Like a dart. Now, if I shot an arrow at you, though, you would probably see the tip of the arrow coming at you. The tip of the arrow is like a dot. Guys, come on, it was funny, now it's focused. The tip of the arrow is like a dot. If you see dots everywhere, it means the field, see B at the top, is out of the page. If you see X's, it's like you're shooting a bow and arrow into the page. So jot that down, please. X's mean into the page. dots mean out of the page. You would literally see something like this. I'll draw what Kian thought he might have seen, or whatever that was. This is what you would actually see. Okay, it would be the same setup. A little 5 by 5 matrix. Okay, if you saw this, it would mean that the magnetic field is out of the page. Okay, B. In this case, this is into the page. All right? So the field is into the page. So John, this is going back to what you were asking about the hands. Take your fingers, the 4 fingers. Those always go in the direction of the field. Since it's into the page, just put your fingers into the page like this. Next. Next. Put your thumb in the direction. Put your thumb in the direction of the velocity. So which way is the force going to be? Out of the palm, right? You see the F magnetic there? Now, watch what happens. Think about this for a second. If the force is this way, the velocity in the particle is going to start to turn this way, right? But what happens to the force? As it turns, the force also turns. And the force is now down, it's going to cause this to move down. But as it moves down, it starts to move this way. What's happening?
It just goes in a circle.
Yeah, so we're using the concept of a magnetic field to keep an object in circular motion. Okay, a very common application if you're doing work in research in electricity and magnetism. If you want a particle moving in some sort of a circular fashion, having a magnetic field present to help you with that is very useful. This particle will literally continue to change, but the velocity vector will change, and so will the F magnetic. It will always be toward the center. So F magnetic is your centripetal force. Think, think, think. Centripetal force was provided by something. Remember, it was always provided by either friction in the road, or the tension in the string, or the gravitational pull for a moon around a planet, or the electrostatic force for an electron around a nucleus. We did maybe 1 or 2 others, I forget, but the idea here is that the magnetic force is providing the centripetal force in this example. Okay? So let's look at an example mathematically of that. A proton is moving through a magnetic field. The field is 2.5 Tesla. If the velocity is 2.5 times 10 to the 7, determine the radius of curvature of the path that it follows. Okay, of the path that it follows. Now, in this case, I should have said into or out of the page, really. I don't know why I didn't say that. That's why I paused. So let's say, for the sake of this, you want to do out of the page? Okay, let's do out of the page. So if 2.5 Tesla out of the page.
What's the difference if you're saying in versus out? What would the value
So,
be different?
remember how we're looking, ready? So, into the page, particle's moving up, means that it's going to turn like this.
So it'll change the
If it
value.
was coming out of the page, and the particle's moving up, it would be going this way. So this is clockwise. When this way, it would curl counterclockwise. So the in of the page, out of the page difference will only affect the direction of curvature, whether it's clockwise or counterclockwise in the end for this example.
Okay, so when you say, like on a test or something,
I'll say into the page or out of the page.
no, but will you write your answer, like you need to find your Tesla, will you say whatever it is out of the page? Does that make sense?
Yeah, you will have to give a direction or it will be given to you in the problem.
Okay, it's kind of like saying a positive, like it's going east or west.
Yes, exactly. That's exactly right. Okay? So out of the page, let's draw a few dots here so we have an idea of what's going on. All right, so if the field is out of the page, the velocity in this case is given as just positive. So let's say that the object is moving right. Okay, it's either up or right because it's positive, so it doesn't really matter in this case. So let's put what is this, a proton? Let's put the proton down here, and it's moving to the right. Again, the field is out of the page. So take your fingers again. Fingers out of the page. This is kind of tough, this is difficult, you have to do it towards yourself. Fingers, just point toward yourself like this. Look at your own fingers like this. Fingers out of the page. Why is my thumb to the right? Because the velocity is to the right. So in this problem, which way is this going to curl?
Under.
Underneath where we're at and back around. Take a look again. Fingers are out of the page because there's dots. Velocity is to the right, so the thumb is to the right. So this is what we have. That means the magnetic field pushes down. because it's a proton. So if it pushes down, ready, watch. Here's a proton moving. It wants to move down. Well, eventually it's going to curl back around. Now it's going to want to move up. When it gets back over here, it's going to want to move to the right. So it's going to be circular motion in this case. That's going to be clockwise. Okay, clockwise circular motion. Again, field out of the page, motion this way. If I'm moving this way, and somebody imagine like if you're let's say a deep end of a pool, and you're on a float, and you're coasting by on a float, and somebody jumps on the float, you're going to go down, but you're still going to be moving right. So you would probably do this, right? You're coasting. Somebody jumps on the float, you're going to move like that. But you're still going to move to the right. So this velocity here is to the right. The field is pushing it down, so it's going to move to the right and down. But now the field pushes this way. So it starts to curl back and back. So what you're going to get is this clockwise motion. Okay, that's the kind of shape it's going to take. All right, anyway, let's get to the math behind this now that we know what's going on. So if the magnetic force is providing the centripetal force, we can set the magnetic force's equation equal to centripetal force. But that's not easy to do without looking. So let's write out what we know. We know this. We know B equals F magnetic over QV. But we want to get F magnetic by itself, because the magnetic force is what's providing centripetal force. So solve for Fm. Now, if the magnetic force is providing centripetal force, we can write the following. And you know this is on your, or it's not actually on your formula sheet. You have V squared over R in yours. Okay, remember mv squared over R is always centripetal force. If magnetic force is providing the centripetal force, these are the same thing. Again, centripetal force is a theoretical idea. Something has to provide centripetal force. Well, since it's magnetic, it means that this equation is equal to this equation. So let's go ahead and set them equal. And our goal here is to determine the radius of curvature. What is the radius of curvature? So what are we looking for? R. Solve for R. Switch it with BQV. Okay, flip-flop R with BQV. What happens to the V's? Good. Leaving what? Yeah, leaving just one of them up top. Okay, there's your formula for this one. One of the V's from top cancels with this V on the bottom, leaving one of them up top and none on the bottom. M is the mass of a proton. It's in the wording of the problem, 1.7 times 10 to the negative 27 kilograms. B is the magnetic field, 2.5 Tesla. Q is the charge of an electron, a proton, 1.6 times 10 to the negative 19. And finally, velocity is 2.5 times 10 to the 7 meters per second. So plug those four numbers in. If you still can't do scientific notation in a calculator, you need to see me. Stop using times 10 if you're still doing that. Use the E button if you're not. Okay, plugging in those four values, what do you get? It's going to be close to 0, close to 1. I can tell because my exponents. Look at your exponents. Negative 27 and 7 gives me negative 20. And the bottom has negative 19, so they're probably going to end up canceling. So we're going to have something that's close on the order of like 0 or 1 or 10. Andrew, go grab some water, please. Look like you're getting tired there. What do you got? What do you got for R?
2.72 10 to the negative 39.
Did you put your denominator in parentheses when you divided? Did you do this? You need to put the whole denominator in parentheses, remember?
9.4.
It's possible I did math wrong in my calculator, but I have a different answer than both of those. Let's go, check. Check your work. Take your calculator out and check.
6.8 times.
Unprepared, negative 10.
What?
What is-
6.8 times 10 to the negative 1.
No. Let me check to make sure. Let me borrow.
Oh, no.
Just kidding? Find the, did you find a mistake? Okay.
I redid it.
What did you get again? Tell me.
1.7
Times 10 to the 7. Enter.
I was gonna do that.
It doesn't matter. Just hit enter. It's same difference.
You're off.
Over parentheses.
Yeah, 2.5 times.
1.6 times 10 to the negative 19.
I'll get it.
2.72 to the negative 39.
Yeah. Let me just. It's possible I did the math wrong, so I got to check my answer.
Wait, what did you get, Ralph?
I'm not going to tell you because you're going to say, "Oh, you have your calculator, Jack." What'd you get, Jack?
Oh, 0.1062.
0.10625?
Yeah.
How did I, wait, so how did I?
I don't know. Let's see. So.
Could it be my
1.7 times 10 to the negative 27 times 2.5 times 10 to the 7. That's what you get for your numerator before?
It's like,
I just
Divided by
he's typing on
the
the.
product of 2.5 times 1.6 times 10 to the negative 19.
Is this weird?
Alright.
Just plug the numbers in the calculator.
0.10625.
Yes, meters.
Okay, so if we're giving something where it's on an order of 10, 10.6 centimeters.
Oh, this should always be centimeters.
No, I was just so we have an idea of what it is. Meters are fine.
Okay.
But 10 centimeters, think about a ruler. Ruler is 30 centimeters. So this has a radius, so it's moving like this. Okay, this is about the path of this proton moving in circular motion. Wow. Make sure you do it. I know I didn't post the homework last night, but I hope everybody did it still.
So when it's positive, it's, how do you know which way it's going?
It has to do with the